To begin with, hashing is an nm by nm square matrix, and it is symmetric, where nm is the number of model parameters. And each element of hashing hij at row I and column j can be written in this form, where mi and mj are two of the model parameters, u is the forward wave field, and delta d is the data residual. Here we ignore the time integral for simplicity. The second term is generally pretty small, and it is usually ignored. So now let's forget about it for the time being. The first term is the so-called Gauss-Newton approximate hashing. Now let's talk about what it physically represents. For example, we consider a 2D model with the source right here and the receiver right here. Mi and mj are two model parameters. Say they are velocities at these two locations. Basically, u is the regular wave field excited by the source. So partial u over partial mi will be the scattered wave field induced by the velocity change at the mi location. In other words, the background wave field u travels from the source to mi, gets scattered by it, and the scattered wave field partial u over partial mi propagates from the mi and recorded by the receiver as a spike right here. And the same thing for mj. In this example, the mj's wave path is shorter compared to mi, so the arrival of the mj scattered wave is earlier than mi. According to this equation, the Gauss-Newton hashing is basically the zero-lag correlation between these two scattered waves. We assume that the source time function, or say the wavelet, is perfectly delta function pulse. Then, aside from the multipathing scenario, the correlation, namely the hij, is generally zero, unless mi and mj coincide with each other. Like this one. As a result, the hashing has non-zero values only on its diagonal, where mi and mj are the same point. So the hashing is a diagonally dominant matrix. But in practice, the wavelet is never as perfect as a delta function. Check out the waveform here. So in practice, both scatter waveforms will be spread out a little bit. Then to have a non-zero value in the hash matrix, mi and mj do not necessarily coincide with each other. Instead, we will have non-zero hashing values as long as mi and mj are neighbors. See the waveforms. As a result, the hashing will be a banded and striped matrix, and the pattern depends on how you sort the grid points. Then let's talk about what kind of information is carried by the hashing matrix. As we just mentioned, we can tell how the scattered waves generated by neighboring points correlate with each other, so we have the information of the finite frequency effects in the hashing. Now let's consider the case when mi and mj are the same points, namely the diagonal element. If we move this point right here, on the trajectory between the source and the receiver, check out the waveform. And then the wave travels shorter. The arrival will be earlier. And also, there will be less geometric spreading, so the amplitudes will be larger, and the hashing element will be larger as well. In another word, the values of the hashing elements can indicate the illumination information, which captures the source-receiver geometry. So far, we have only discussed the monoparameter case. So what about the multi-parameter FWI? For example, in the viscoacoustic case, if we consider both velocity c and the attenuation gamma, the hash matrix will have a 2 by 2 block structure. The diagonal blocks are pretty much the same as the monoparameter case. Let's focus on the off-diagonal blocks. In particular, let's consider the element on the diagonal of an off-diagonal block. then Mi and Mj represent the velocity and the attenuation at this specific point I, respectively. So Mi becomes Ci and Mj becomes gamma I. Partial U over partial Ci is induced by a velocity scatter, and partial U over partial gamma I is induced by an attenuation scatter. This hashing element Hij is a zero-lag correlation between them, meaning how similar they are with each other. So a large value in the off-diagonal block means that the velocity perturbation and the attenuation perturbation can produce similar seismic waveform perturbation, and thus it is difficult to tell if the data residual should be attributed to velocity or attenuation, which leads to the crosstalk. So the Hessian matrix has the crosstalk information. Finally, let's check out the second term of the Hessian. Physically, it represents the wave field first scattered by Mi and then scattered by Mj, weighted by the data residual. So in this way, this full Hessian contains the information of the second order scattering. Basically, these are the four pieces of information carried by the Hessian matrix.